In this part, we want to see how to get the amount of energy stored in a capacitor. So before we talk about a capacitor, let's talk about a mechanical system which consists of a floor and a ceiling and a block, a mass on the floor. So the block initially is located on the floor. And let's get an external agent and make this external agent move the block, raise it from the floor, and then in the final position we put the block on the ceiling. So the external agent applies a force, F external, in the upward direction. Gravity is acting downwards during the whole motion. For which position of the mass does the system have larger energy? And is the work done by the external agent positive or negative? Well, the force the external agent is doing is upwards, and the direction of motion is upwards, so the work is positive. And of course we know that when a mass is at a higher height, the energy of the system is larger. So when the external agent does positive work by raising this mass to the final position, then the energy of the system gets larger. So the external agent is basically delivering energy to this system. So in the final situation, if the external agent raises many masses to the ceiling, then this configuration where you have many masses on the ceiling is a configuration of higher energy. The amount of energy stored in the system is a large value, and you can use this energy by releasing, for instance, the masses, letting them fall down, attaching them to a rope on a pulley, and then you can make this pulley with a rope rotate something or carry something else or do something useful with it. So this system stores energy. The same thing we can do with an electric system, a system consisting of two conductors. Initially they are uncharged, so the amount of positive charge is equal to the amount of negative charge. So initially, let's say these two conductors are neutral. The total charge is 0. And then let's start to take one negative charge from this conductor. The external agent moves it from this conductor and puts it onto this conductor. This is what the situation would be after that happened. You have one positive charge remaining here and one negative charge extra on this plate. Now, I don't need to put all these neutral charges since they always exist. I'm going to take them off, and I'm only going to show the extra charge. So after some time of moving negative charges from this plate and putting them onto this plate, this is what the situation would be. You'll have a charge small q plus small q on this plate and minus small q on this plate. And during the intermediate step, we're taking an amount of infinitesimal amount of charge minus dq, where dq is a positive number and minus dq is a negative amount of charge. So this is an infinitesimal amount of negative charge. We keep on taking it from the positive plate to the negative plate. That's how we can charge the capacitor. So this is what the finally fully charged capacitor looks like. This plate has a total charge plus big Q, and this one has a total charge minus big Q. Now the question we want to find is how much energy is stored in this system. That's the question we want to answer. So let's look at the intermediate step. Let's look at the situation where the charge is not the maximum value, it's some intermediate value. And in the initial situation, we have the charge minus dq on the left plate. And in the final situation, we have the same amount of charge on the right plate. Now, during this transformation of the charge from this plate to this plate, the amount of charge on the capacitor plates hasn't changed much because this charge is infinitesimal in amount. And this charge is a large value relatively. So we can say that the charge here remains Q and minus Q and minus Q. Now this configuration has a certain amount of energy stored in it, U initial. This configuration has a certain amount of energy stored in it, U final. What is the difference, U final minus U initial? Is it positive or is it negative? Well, let's think about it in a bit more detail. When you take an amount of charge minus Q minus dq from the positive plate and put it on the negative plate, where does this negative charge want to move to when you let it go? If you put it in the middle of space here, where does it want to go? Obviously, the electric force on this charge minus dq is this way, to the left. So this means that the system has a higher potential energy when the charge is located more and more to the right. If you let this charge go from rest at this position, it has zero kinetic energy initially, that means it must have some potential energy. And then when the charge goes to the left, the kinetic energy gets bigger and the potential energy of the system gets smaller. So as this charge goes more and more to the right, the potential energy of the system is getting larger. So the external agent, when it applies a force on the charge to move it to the right, what is the direction of the external agent force? Obviously, the external agent has to apply a force to the right to make the charge go to the right, because the charge doesn't want to go to the right. Now, the work done by the external agent, we showed that it's equal to the change in energy of the system. So the work due to the external agent is the integration of F dot dr. Since F is in the same direction as the direction of motion, then this is positive. So the work done by the external agent is positive. So the difference in energy between the two different configurations is positive. You can also write the work as the change in energy as the negative of the work due to the electric field. And the work due to the electric field is negative because the electric force is to the left, the direction of motion is to the right. So the work due to the electric field, this integration is negative. So you have a negative and a negative, you get positive. Same result. So let's also see how we can write the difference in energy between the two different configurations. We'll call it du because it's an infinitesimal difference in the energy, because we're only moving a small amount of charge dq minus dq. So we showed before many times that the difference in energy is the work due to the external agent. It's the negative of the work due to the electric field in the case where there's no change in kinetic energy. But also it's the charge times the potential difference. The charge that we're moving is a negative charge. It's minus dq. dq is a positive number. So the amount of charge we moved is minus dq. And the potential difference in the potential in the final position is V2. And the potential in the initial position is V1. Now, V2 minus V1, is it positive or negative? V2 minus V1 is negative because the electric field goes from a region of high potential to low potential. So the second plate is at a lower potential than the plate number 1. So V2 minus V1 is a negative number. So what if we multiply this minus sign in to reverse the V2 minus V1 and make it V1 minus V2? That will then be a positive quantity, and dq is a positive quantity. So then we showed that also the dq times v1 minus v2 is a positive amount, which is as we expect. The difference in energy is positive. The energy in this configuration is larger than the energy in this configuration, and it's larger by this amount. Now, we found that the infinitesimal amount of difference in potential energy between this configuration and this configuration is the charge, the magnitude of the charge, times the difference in potential between the two plates. How can we replace the difference in potential between the two plates by something else? We know that as the capacitor is charging, there's always a relationship between the difference in potential, the charge on the plates, and the capacitance. Delta V is Q over C. I can write du as Q over C dq. So if I want now the total energy stored in the capacitor, how could I get that? I'll integrate from 0, when the capacitor was completely uncharged, the charge was 0, to the maximum value of the charge big Q. So I want to integrate this quantity from 0 to big Q. Now this C, can we take the capacitance outside the integral? Well, during the charging process, since the geometry of the capacitor hasn't changed during the charging process, and we know that the only thing that will change the capacitance of the device is if you change the geometry. So the geometry stays the same, the area and the distance between the plates. So the capacitance is a constant during the charging process, so you can take it outside of the integration. So you're left with integration of Q dq. Integration of Q dq is Q squared over 2, and then you substitute the upper limit big Q and the lower limit 0. Get this final result. So this then is the total amount of energy stored in the capacitor. And this is a summary of what we just found. We found that if you have a capacitor that has charge plus Q and minus Q, the total amount of charge stored in this capacitor is Q squared over 2C. There's different ways to write down this total energy of the capacitor, and one way we can do it by replacing C by Q over delta V. If we replace C by Q over delta V, then one of the Q's will cancel, and then the delta V will go in the numerator. So you get 1/2 Q delta V. You can also get a new form of this by replacing Q by C delta V. So now C delta V, and then you have another delta V, so delta V squared. We can write down also the energy stored in the capacitor as 1/2 C delta V squared. So to summarize, these are three different forms that we can write down the total energy stored in a capacitor. Whichever one you use depends on the given in the particular problem that you're using.